Hey guys, this is Sean with Alexander Tutoring, and I have a very special video for you today. It's going to be on exponential growth, the same exponential growth that all high school students do around junior year. But we're going to use real life data, the coronavirus. So we're going to try and come up with a model that predicts the number of infected cases over time, assuming an exponential curve. So for all of you that thought that they would never use their math, now's the time. We're going to come up with a math model, and I hope you like it. So, what we all learn around junior year is that all exponential functions are governed by the equation y equals a constant, usually your starting value, times b, another constant called your growth rate, times time, the amount of time that has elapsed. Excuse me, not times, to the power of t, the amount of time that has elapsed. So our challenge is going to be to find the constants a and b. And in order to do that, we're going to need two x and y values. And I'm taking those x and y values from the CDC, which I've written above here. And those values are going to be, on March 15th, there were 169,593 confirmed cases of the coronavirus. On March 20th, 5 days later, there were 275,597 cases. So we're going to use those numbers to determine the constants a and b to try and come up with a model that will predict the number of cases going into the future. Okay, so basically, this is point number 1 and point number 2. The first thing to recognize is those are 2 points on a graph. We're going to call March 15th equivalent to t equals 0. And then the output y is 169,593. And point number 2, March 20th, we're going to call 5 days later than what we call t equals 0, or 5, t equals 5. And the number of confirmed cases from the CDC is 275,597. Okay, so those are 2 points on the graph. We're then going to plug them into our standard exponential growth function. Okay, so we'll start with the first data point. So y equals 169,593 when, okay, then we have a constant to be determined times b, next constant. But t, we know that's 0 because that's our starting point. We're making March 15th our starting point, so we're going to call that t equals 0. Now, for those of you that know me, anything to the 0th power is equal to 1. I could talk about that all day, but I don't have time right now. So let's just assume that anything to the 0 is 1, and we're left with a equals 169,593. So we've determined our first constant a, which is usually like the starting value. That's like the number of confirmed cases that we're starting with on March 15th, okay? Okay, so we know what a is, so let's put that into our formula. And we still need to know b. So we're going to use our second data point, 2, that on March 20th, 5 days later, the number of confirmed cases was 275,597. Okay, so that's our y value is 275,597 equals 169,593, a, which we already figured out, times b, which we're trying to figure out. And this is 5 days later from the 15th on the 20th, so t is now 5. Okay, now we just need to solve for b, and then we'll have our mathematical model. So how do we solve for b? First, I'm going to divide both sides by 169,593. Hopefully you watched my video on what you do to one side, you do to the other. Come down the line. And then, excuse me, I'm going to use my calculator. I cannot do this in my head either. So we have 275,597 divided by 169,593 on the left-hand side to get, that's not right, let me try that one more time, 275,597 divided by, there we go, roughly 1.625. These cancel to equals b to the 5th. Okay, how do we isolate b when it's to the 5th power? The answer is we take the 5th root of both sides. And what's the best way to do that on your calculator? Again, this could be another video entirely, but on your calculator, the easiest way is to use the power of 1/5. So b to the 5th to the power, we're going to take each side to the power of 1/5. If you have questions on this, just let me know. Okay, and on the left-hand side, the rule is you multiply the exponents, so 5 times a 5th is just 1, or just b. That's why it solves the equation. And then we're going to do our previous answer to the power of 1/5 to get roughly 1.102. Okay, so we figured out A, and we figured out B, which means we figured out our equation. We're going to plug them both into this guy. So the number of infected cases, Y, equals A, 169,593, our starting value, times B, this is called a growth rate, the amount by which it grows for each iteration of time, in this case day, each day that goes by, to the power of t. And there we go, guys. That is our model for predicting the number of cases in the future. So first, let's test to see if our model actually even works. So I happen to know from the CDC website that today, on March 22nd, the number of confirmed cases is 337,469. Okay, so let's see if our model predicts that, because we gave up on the 20th. So what would t be for March 22nd? Again, what we called t equals 0 was March 15th. So t for the 22nd would be how many days past the 15th it is to the 22nd, which in this case is 7. Okay, so we'll just plug 7 into our formula for t right here. So we get y equals times. Okay, we're testing our formula to see if it predicts today's number correctly. Okay, so we have 1.102 to the power of 7 equals that times 169,593. Y equals 334,673. So check that out. We're going to pair these two numbers. The one on top is the actual number given by the CDC, and the one on the bottom is one we predicted. Oh, excuse me, pointing in the wrong place. Let's try right there. Boop, my bad. Okay, so our model predicted 334,673 cases. The CDC says there's actually 337,469. So they're pretty close. You know, it's not perfect, obviously. There's lots of errors. I should say that the reason I chose two kind of close points in the curve, the 15th and the 20th, to come up with our numbers is that I think that more recently there's been more test kits available. So I think more recent numbers are more accurate as far as conducting our model. Now to end the video, I want to predict a couple of numbers using our model. Again, this is this guy. Given that we found that it's semi-accurate, if the curve continues, now that's where we're all sheltered up. We're trying to get off the exponential curve. We're trying to get off that curve. But if it continues, let's see what we can expect. So how about we look at April 1st? So today's the 22nd. 30 days, so 31 days in this month. So from the 15th, it's 16 days to the 31st, so 17 days to April 1st. In our model, it's 17 days. Okay, so let's see how many cases we get in that case. So t is 17. So we get y equals 169,593 times 1.102 to the 7th. Okay, and then I'll use my calculator. Times 169. Oh, I'm sorry, not the 7th. My bad, guys. We did that earlier. I meant to say 17. So again, sorry about that. 0 is the 15th of this month. So we're trying to go to April 1st. which is 17 days from the 15th. Let me try that one more time. Okay, so to the power of 17 was that times 169. Okay, so on April 1st, our model predicts there will be 883,800 cases of the coronavirus. So we're really starting to see what exponential growth means. It just keeps getting bigger and bigger and bigger. For our final calculation, before I let you guys go, I'm going to calculate what the number should be on June 1st, roughly, or the beginning of summer. So for the beginning of summer, now I'm ballparking. So it's roughly 15 days from our starting point, mid-March, to April, and then April, May. So that's 60 days plus 15. Let's just say 75 days from now. Okay, let's run it through the equation. Y equals our starting value 169,593 times 0.102 times to the power of t. Now we're going to June 1st, which is roughly 75 days from now. Let's see what we get for this case. So we go 1.102 to the power of 75 times 169,593 equals, wait for it, number of cases on June 1st, 246,834,788. That is the power of exponential growth, my friends. Now, I'm not saying that's going to happen. I'm just saying that if we continue our curve out to infinity, the number gets big really quick. So that's where we're all buckling down, hoping to get off the exponential curve. I'll update you as time goes on where we stand next to our mathematical model. Again, this is something you could all do with high school math. I hope you enjoyed and found it relevant to your day and your daily life. Okay, take care. I will see you tomorrow for the next video. Bye.